So for example, if I was to say, hey, tell me about that function. In particular, maybe its domain. What could you tell me? Okay, because of this. Okay, there is a reflection. It's on the inside of the function, the inside of the logarithm, so it is over the y-axis. So there's a y-axis reflection. I'm not going to attempt to like list these in order for right now, but there is a y-axis reflection. What else? There's also a range thing. Yep. That plus one shifts it up one. How about the two out in front? Yep. And the four? This would be another way to write that thing. So it's a horizontal shift, right? Even if we're not sure if it's left or right, let's just say that it's a horizontal shift for now, okay? With the shift and the reflection in the same direction, remember that's the case where things get a little bit, dicey about like which way it goes because, do you move it and then reflect or do you reflect and then move it? And I agree that can be kind of hard to keep up with. So that anyway, which of those affect the domain? Those two are relevant. Those two don't have anything to do with the domain, right? It's a vertical stretch. It's a shift up one. Those don't impact the domain then. So how can we figure out the domain for this function? Set 4 minus x equal to 0, which means that x is equal to 4. And then what? And then what? So 4 is important then, right? What happens at 4? That's where that vertical asymptote is. Logs have a vertical asymptote. For this one, it's at x equals 4. Okay, so what ended up happening is that things shifted to the right then, right? Because it used to be at 0, now it's at 4. Okay, what else do we need to know? That's what I know right now. What do logarithms look like? Something like that, right? So what I need to know is it over here, like 4 to infinity, or is it over here, like negative infinity to 4? Negative infinity to 4, okay, we could get that from the fact that there was a reflection across the y-axis, right? So it's facing the other way. If we're not sure, not as comfortable with that part, I could just do the old inequality thing and say, hey, here's 4, here's a vertical asymptote. If I take something over here, this would be 2 times the log base 3 of 4 minus 0. Whereas if I take something over here, this would be 2 times the log base 3 of 4 minus 8, so negative 4. Now, I know this looks, a little more complicated than, it's not just like 1 plus 2 or something. But does this exist? Is this a real number? If you're not sure, grab your calculator and punch it in, right? The thing to look at is not the times 2 or the plus 1, but the log. Can you take the log of 4? Yeah. Can you take the log of negative 4? No. That means the domain's to that side. Oh, sorry. There you go. Okay, the point I'm trying to make with all of this is that we have some options, right? We could solve this as an inequality directly right off the bat. The kinds of things you can take logs of are positive numbers. So I can say 4 minus x is greater than 0. I would get x is less than 4. That means this is the domain. I can solve it as an equation, which tells me where the vertical asymptote ends up after we do the stuff. Well, then I still need to know which side. Okay, I can think of the which side question as how did the transformations work? Reflected that way. I can think about it graphically, right? And maybe, I want to back some stuff up, but I can look at the graph and see, it lives over here. Okay, well, it lives over here. That means it's defined over here. That means the domain is this. Or we could, kind of brute force it and just say, like, what happens here? Yes or no, does it exist? What happens here? Yes or no, does it exist? Right? Okay. Everybody feel good about that? Okay, cool. All right. So, just like we saw with rational functions and square roots and stuff, this domain question ends up being important. We'll see this as we get into solving equations later that, we start working with things that have a logarithm, and at some point we might end up taking a log and turning it into an exponential to solve. When we do that, we kind of change something about the, big picture of what's going on and maybe run into some weird stuff with this domain issue. So we need to be able to kind of assess where things are defined. Okay, and that would be the sort of short version of getting the domain of a function. Must be positive in order for the function to be defined. And that's what we've worked through here. Okay, do you have any questions? Okay, cool. Quiz tomorrow. Yeah. Everybody heard me say quiz tomorrow, right? Okay, go ahead.
So since it was 4 minus x.
Yeah.
How can we shift it to the? You said we shifted to the left.
Yeah. So that 4 minus x. Right. You can think of as negative x plus 4. When the shift and the reflection happen in the same way, like that, you kind of need to think of the negative. Oh, sorry, you can't see what I'm writing. You kind of need to think of the negative that way. So it's either a, like this would appear to shift to the left, right? So it's either a shift to the left, and sorry, it would be facing this way, shift to the left and then reflect it, which puts it out at 4, like if this is the y-axis, right? That stays put, so you shift it and then reflect, and it kind of swings around like that. Or doing like this, you shift to the right, and then you reflect it where it is. Yeah, so that's the case where those two things are happening together, and like more so if there's a stretch or something involved too. That's where everything starts to become kind of dense, right? And difficult to sort of figure out, one at a time what they all are. Which is why it's good to have, sort of some, be able to like go a little deeper into it when I'm not quite sure which way those end up. Yeah. Okay, good. Yeah, all right. Okay. That's the wrong thing. Okay. So, properties of exponentials and logs. This is a really, really quick review of the stuff that was in the video for this week, but just to make sure we're all on the same page. If you want to multiply 3 squared times 3 cubed, what do you do? Other than just, type it into a calculator. Like, how do you combine the exponents? You add. This means 3 times 3. This means 3 times 3 times 3. And if you're multiplying, you just add them together. That's a 3 also. That looks kind of squirrely. But 2 here, 3 more here. That's 3 to the 2 plus 3. Or, sorry, I don't know what's going on. 3 to the 5th. And this would be true for anything where the bases match, right? So it's multiplying like bases. By the same notion, if you divide like bases, you subtract. This is 5 copies of 3 divided by 2 copies of 3. Okay. So 2 of them cancel and you're left with 3 in the numerator. So that's what it would end up being. Well, how would that be different? Mm-hmm. Yeah, 3 squared over 3 to the 5th. You would still subtract, but top minus bottom still. So you'd still have, sort of 3 copies of 3, so 3 cubed that like overhang, right? It would just be in the denominator instead of the numerator. Yeah. For multiplication, for products, it doesn't matter because addition works the same way either way. For division, it does matter, top minus bottom. So that's the quotient rule. And then power raised to a power like 3 squared to the 4th. This means 4 copies of 2 copies of 3, right? So 3 times 3, 3 times 3, 3 times 3, 3 times 3. So how many total do we have? 8. And another way to get 8 from 2 and 4 is 2 times 4. This is really just kind of a shorthand version. Sorry. This is really just a shorthand version of what's happening here, right? This power means 4 of those written out, but each of those is, going to be 2 plus 2 plus 2 plus 2, so you end up with 8. I'm not really sure what I should highlight here. Maybe those things. I don't know. Okay, so those are things that we already know, or in theory already know about dealing with exponents. When we translate those same things into statements about logarithms, well, for starters, let's remind ourselves how log works, just because maybe we're still getting used to it a little bit. We want to make sure we're okay with that. What's the log base 3 of? Well, hang on. Let me start from the other side. 3 squared is 9, right? Okay. How do you write that as an equivalent logarithm? The log base 3 of 9 equals 2. So what the logarithm gives you is the power, right? The exponent. The value of a log is an exponent that we didn't know before, or we didn't know otherwise, right? And the idea is, basically what we're working up to is something like this. 3 to, some unknown power is 9. Well, if I take that same information and rewrite it as a log, then what happens is we get the log base 3 of 9 equals, well, whatever that thing was that I didn't know, only now I've turned it from sort of a guessing game, right? Like, I hope I can figure out what power of 3 that is. And of course, 9 came, but I've turned it from like a guessing game into just an operation, right? A thing that I can evaluate, that I've got, methods and techniques for, or a calculator button anyway, which is 2. Right, so what logs do is give us a way to find a missing or unknown exponent. Then, like that's how they, make our lives better. Is we can do that kind of thing. Again, though, this is the idea. And, if this is something that hasn't quite clicked for you yet, as you do this, as we get into solving equations and stuff, even if it's, memorizing for the time being some like pet example like this, and just sort of carrying that around and kind of trying to, mimic stuff, right? The base, the thing that looks like the answer, and then the exponent, right? The base, the exponent, the answer. Being able to just rewrite the thing ends up being a big portion of what we need to do. Okay, so with that in mind, if a log is an exponent, then what log properties say about these same things is that if we take a log of a product, like what happens is that turns into the sum of the separate logs. And there's really nothing, I mean, just like there wasn't anything special about the 3 here is the base, or the powers that I chose. Like, I'm just picking something to write it down, because otherwise I'd have to pick things like, write everything in terms of A and B and whatever. And then, people get kind of lost in that. So I'm just choosing something to write it down with. But the point is that the log of a product turns into the sum of the separate logs. This multiplication, well, what the log is going to do is tell me about the exponent, right? It's going to find the exponent. So these are the sort of component logs here that I'm breaking this into. This addition is this addition, right? So if logs are powers, then the log of a product becomes the sum of the logs. This is weird, right? Like this feels different than it is from other stuff that we're used to dealing with. But that's the product rule for logs. Let me put that above it. Similarly, we have a quotient rule for logs. It says the log of a quotient, and again, whatever, 4 squared over, I just need something there, right? This division is like this division, right? And that means that if the log is going to tell me about the exponents, what happens is we get the difference. Oh boy. Okay. Everybody just bear with me for a second. Oh no, I've forgotten how to make letters altogether. Okay. We're all going to be fine. Okay. So that's quotient rule. Power rule. Well, in the same way that a power is always, especially like a whole number power, it's the easiest way to see it anyway. In the same way that a whole number power is like a number of copies of the thing. When we do that in the context of a log, and when, again, what logs do is tell you about a power or an exponent. If we take the log of 5 cubed, and if I think of that 3 as being like 3 copies of 5, right? Then what happens is I can bring that exponent, that power that's inside the log, I can bring it down. And when I bring it down, it becomes like a coefficient, right? So it becomes like a number of copies of whatever that power is. In other words, what this log is doing is asking, how many of, and all these, I didn't write a base, so that means the base is 10, but it works the same for whatever the base is, right? It's asking how many copies of the base are in this number, right? Well, whatever that is, if I cube that thing, I'm gonna have 3 times as many of them. That's what this says, okay? But it works, whether this is a whole number or a fraction or positive or negative or whatever this exponent is, we can do this kind of thing and bring that exponent down. And one way to think about it would, again, just be, this several times, right? Think of this as 5 times 5 times 5, and it becomes the log plus the log plus the log, or 3 of them. Now again, these are things that are counterintuitive, right? These are not how anything else that we've ever worked with or will ever work with is not how other things behave, right? So we need to be aware of that and careful about that. This also means that things that other stuff does, English, things that happen with other things don't happen the same way with logs. For example, and this one's important and almost always catches some people, logs do not distribute in the usual way. That's where 2 exclamation points. The log of x plus 1 is just the log of x plus 1. It is not the log of x plus the log of 1. Now, sometimes that's a bummer because it makes life a little harder maybe in some circumstances. But the flip side of that is that we do get all these other properties that we just talked about that make life easier in some circumstances. When a log does not distribute, you cannot do this. If you even think about the domain, this should make sense. What's this plus 1 do? Just to the left one. So the domain of this thing is -1 to infinity then, right? Well, if the log distributed like this, that would still be true here, but can you take the log of, something like -1/2? No, right? So the domain mismatch between what's over here and what's over here should be, among the things that point us to the fact that, these are not the same. Okay, so logs, the upshot is that logs don't play nicely with addition or subtraction. They don't split up over that. They don't distribute. They don't give us a way to simplify anything involving addition or subtraction in the argument of the log. But they do a lot of cool stuff with multiplication and division. And again, these things are kind of the reason that people developed the logarithm in the first place, was to be able to break stuff like this up to do arithmetic back in ye olden days when you had to do it by hand. But these also give us some good techniques and stuff that we can use in solving equations and working with logs. Okay? Okay, so to make sure we've got the hang of working with these properties, first example here, simplify some stuff using exponent rules. Do roll, give you guys a few minutes to work on this. All right, what's 5 to the x times 5 squared? 5 to the x plus 2. Okay, cool. It's kind of just a cool thing as functions too. 5 to the x times 5 squared, if I think of that as a function, right? Exponential growth, 5 to the x, times 5 squared, which is 25, right? That's like a vertical stretch by 25, right? It's on the outside. 5 raised to the x plus 2 is on the inside, that would be like shifting 2 to the left, right? So what this says is that, hey, 5 to the x times 5 squared, if you take 5 to the x and stretch it by 25 vertically, that's the same thing as if you just took the function and slid it over a little bit. That's a cool thing that exponentials do, is that, you know, when the bases match like that, when the stretching factor matches, it's like the same thing as just sliding it over. Okay, but that's how the exponent properties would work there. What about 3 to the x divided by 9? Well, if we're going to do the same kind of thing and rewrite it as, you know, a like base thing, then I need to start with 9, which is 3 to the okay, which will make this 3 to the x minus 2. Okay. For the moment, just think, I know that, you know, to some extent, this may seem kind of like, you know, why is this not okay, right? The answer is it is, kind of. Right? I can think of this as, again, 3 to the x divided by 9, so that's a vertical, you know, squishing thing, right? Translating it to this is a shift to the right. So, like, there's nothing wrong with this, but what we're trying to do is kind of lay some groundwork for some stuff later on. And again, just reinforce these exponent properties. But I didn't want everything to be, you know, just a x to the 5th and x squared or whatever. Okay, 2 to the x to the 3rd, which is the same thing as 2 raised to the 3x, times 4 to the x, which is the same thing as 2 to the x, right? So 2 to the 3x times 2 to the 2x, or 2 to the 3x plus 2x, or 2 to the 5x. There will be times that we may need to lean on exponent properties like this a little bit, or, you know, whether we need to or not, they might make life a little easier. So again, I'm just trying to kind of make sure we have those down. So this is how you can use this here, right? This is a power raised to a power. So apply the power rule thing. X times 3 is 3x. 4 to the x, I'm just rewriting as 2 squared so that I have them in terms of a like base, right? So that then I can combine stuff. 4 is 2 squared. 4 to the x then is 2 to the 2x. And then we can combine and get them as a single thing. Now, again, the idea is that if I'm trying to solve an equation involving this, my life is probably going to be a lot easier if I turn it into this thing first and then try to do the stuff we need to do. Okay. Everybody feel okay about those? All right. How about some logs? So for starters, just evaluate these. So just, you know, more practice reinforcement with that. Okay, what's the log base 4 of 16? 2. Okay, what about the log base 6 of 1 over 36? Negative 2. Okay, ln natural log of e to the 9th. 9. ln means log base e. E is e. So the natural log of the power of e is just whatever the power of e is. These things are inverse functions, right? The natural log or log base e and the power of e, those are inverses, so you just end up with power. Now, what happens when you get to the log, no base written, so common log base 10 of 10 to the 5,237th power? Did you get some kind of error message on your calculator? Okay. Desmos says it's undefined. It's not really undefined. What's actually happening? About how big is 10 to the 5,237th power? Real big. Yeah. It's a 1 with, well, 5,237 zeros after it. Okay. Your calculator doesn't know how to deal with that, right? Like, there's not enough memory to store that thing, so your calculator just says, like, forget it, I'm not doing this, buddy. And Desmos does a similar thing, and depending on how it's programmed, it gives some different kind of error message. Like this says undefined. What did yours say? Error. Error. Okay. A computer might say something about like an overflow, right? That like it doesn't have enough memory to store that number. But what's the log base 10? Log base 10 of 10 to the 5,237th power. How many tens are in 10 to some power? Well, how many tens are in 10? 1. Okay, so how many tens are in 10 squared? How many tens are in 10 cubed? So how many tens are in 10 to the 5,237th? Exactly. Even if your calculator's not smart enough to handle that number, right? Because calculators aren't smart at all, right? They're dumb. They just, do arithmetic. You're smarter than that. Just sometimes we don't want to do the arithmetic, right? Another way to look at or think about what's happening is that this is like an application of that power rule thing, right? I could bring that exponent down and treat it like a coefficient. And then the question, like the thing I asked the calculator to do, is the log of 10. It can handle that. The log of 10 is 1. The same thing's true with these others that we've looked at, right? Even when we could do it directly. The log base 4 of 16, well, 16 is 4 squared, right? And what the log base 4 answers for us is how many 4s are in 4 squared? Well, how many 4s are in 4 squared? 2. 1 over 36 is 6 to the minus 2. How many 6s are in 6 to the minus 2? Negative 2 of them, right? So what happens is that when the base of the log matches the base of the, if I can rewrite the thing inside the log as a power of that same base, and the problem is that we can't always figure out how to do that, right? Here it's just kind of lucky that I know that 16 is 4 squared, right? This is like me noticing something. If this number was a lot bigger, well, I might not notice it in the same way. But when I do, those effectively cancel out, and what we get is just the power back, because again, I could think of this as using this power rule idea to bring the exponent down. The same thing's true here. The natural log of e to the 9th. That's like 9 times the natural log of e, but the natural log and e are inverses to each other, so that's just 1, which is how we get to 9. Okay? So then I know that the log base 2 of 2 cubed times 2 to the 5th is 8. How do I know that's 8? Because the powers were 3 and 5, and you're multiplying them together, so what do? You add them together. Right? The like long way here, if I wanted to be really explicit about writing everything out, that's 2 cubed plus 2 to the 5th, right? That's the product rule. And then each of these, I get to do a little power rule thing, or, you know, that's if I don't recognize that the bases match, I guess. And I get 3 and 5. And then that's 3 plus 5, and 3 plus 5 is 8. Okay, so what's F then? 3. 3 to the 5th divided by 3 squared, so that's 3 to the 5 minus 2, that's 3 cubed, and then you're taking the log base 3, so what's left is just, okay, how many 3s are in 3 cubed? 3. Okay. Everybody feel okay about things so far? Anybody have any questions about anything at this point? Yeah. Yeah. So there are a few ways we could go about this, right? I could just think about simplifying this thing first. Since you're dividing, you subtract the powers. And then again, the question that the log base 3 answers is how many 3s are in this? And it's 3 cubed, so the answer is 3. Yeah, just that exponent, right? Yep. Okay. So certainly all these properties that we've been talking about, they all work when the bases match, right? Logs where the base of the log and the base of the exponent match, like that's sort of the friendliest version. We can just, you know, as long as we sort of notice or can figure out what the powers are, like we did here, then, you know, easy peasy, just write it down. No big deal. I don't need a calculator or anything. I can just, you know, sort of spot what it is, right? Which is good for things like this where the number's too big for a calculator to manage anyway. Right? But the cool thing is that, another cool thing is that these log properties still work even when we don't have the same sort of nice matching thing going on with the bases. So what that lets us do is combine or split up, we're going to call that expanding or condensing, algebraic expressions as well. So the log base 2 of 4 times x cubed times y, this is a lot, right? But log properties, because this is all combined with, you know, different versions of multiplication, right? Log properties give us a way to break this up into smaller and simpler pieces. So this is 4, and, you know, even if you like just read this aloud, right, and kind of narrate what's happening, 4 times x cubed times y, that's got 2 multiplications in it, right? 4 times x cubed times y. Log properties say I can break multiplication up, and when I do, where I had multiplication before, instead I get addition. So this would be the log of 4. It's a log base 2 because this was base 2, right? We'll come back and look closer at things and see if there's other stuff we can do, but that's using the product rule on that multiplication, right? Turns into addition. The log base 2 of x cubed. And then there's another multiplication here, which I can again break up and turn into addition by the product rule. You get the log base 2 of y. Now, yes, there are 3 log terms now, but if I look at any one of them at a time, I'm not as, you know, intimidated by this as I am by this whole thing, right? Like this is what logs do for us. So now we just kind of zoom in and look at the individual pieces and ask, like, can I do anything else with that, right? Can I clean that up any further? Can we do anything else with the log base 2 of 4? Well, first of all, it's just a number, right? The base is a number, the thing inside the log is a number. This is just a number then. So the question is this a nice round number that I can just write down, or is it some big ugly decimal mess that I don't want any part of? And it's 2. So I'll just write that as 2 then. Now, if that had been the log base 2 of 3, where it's not a nice round number, right? It's not something that converts to a nice fraction. It's just a big, ugly decimal mess. I would just leave it like that. This one cleans up nicely, though, so I'm going to go and clean it up. Okay? Okay. And you'll notice that, as you get into problems in homework and stuff I give you, like it should become pretty clear the times that I want you to, sort of evaluate the thing and simplify it, and the times to leave it alone. But we'll talk about that more as we go. Okay, plus, that's this one, right? Now the log base 2 of x cubed. Now, first of all, do we know what x is? It's just x, right? Okay, so we're still going to have x in our answer, like it's just a thing. But can I do anything else to simplify this piece? Or is it already kind of in the lowest terms we can go? It's got a power inside it, right? And what log properties let us do is break up multiplication and division and powers. Those are the things we can simplify. This has a power, so we can take that and we can bring it down front. And so what's that term going to look like? 3 times the log of x, log base 2. Now again, without some context for what x is, I can't do anything else with that, but I can rewrite it like that so that this is sort of in the simplest terms I can give it. And what about the last one? Stays the same. I don't, again, have any context or meaning for what y is. Y is just some parameter, right, that we're working with. It's already in lowest terms because it doesn't have any products or quotients or powers in here, right? So we just leave that like it is. Okay? Okay. So that's expanding, taking a single kind of messy log and splitting it up into several smaller, simpler pieces, right? And just working each of those down kind of as far as we can take it. We got a couple minutes left. Y'all give me a shot. Okay, so the more stuff that's going on here, the harder it gets to sort of do it all in one go, right? And just sort of see what everything's going to turn out to be. So my advice there would be to start by looking for kind of the biggest thing happening, right? So if I look at this thing as a whole, what about that feels like the biggest part of all the stuff that's going on? Yeah. The thing that jumps out at me first right? Like if I was gonna, somehow like try to describe that to you and get you to write it down, a good place to start would be like, well, first of all, it's a fraction, right? And that means there's division happening. And division inside a log turns into subtraction. Now, once you do a few of these, you'll probably start to get to the point where you can kind of spot some things coming, right? And like do a couple things at once. But the biggest thing I see there is that subtraction, right? Division there, so subtraction of the separate logs. And then again, we kind of zoom in, right? Like I forget about this for a second and just look at that part of things and think about, okay, now what else can I do with this? So what else can we do with that? Yeah, the next biggest thing, right? The biggest thing happening here would be that multiplication. The exponents only apply to one part of it, not the whole thing, right? It's not the whole thing squared, the whole thing to the fifth. It's this piece squared, that piece to the fifth. The multiplication joins them together though. So break that up next. And again, as you get, more used to it and start to feel, more comfortable with what's going on, you can start, maybe doing more than one thing in one step or whatever. But this is write as many or as few steps as you need to kind of get to where you're going kind of thing. Okay, everybody good so far?
Would you have to, like, group the two that are together?
So if it's relevant, yeah, you would want to treat these like they came from the same place. So the way this one's going, it's not going to matter. If they had been in the denominator, then I would want to have those grouped because they would end up both being negative. Yeah, so that's a really good point. And I might just throw a set of parentheses here because these came from this one thing, right? Turned into these two things. Now those pink parentheses aren't really doing anything here, but they could be sometimes. Yeah, good point. Okay, what's the natural log of e squared? 2. The natural log of x to the fifth can be written as 5 times the log of x, and the log of y cubed, 3 times the log of y. So that'd be this thing sort of fully expanded. Okay, that's it for today. Get started on homework. Tomorrow we'll look at going the other way and then see, why we care about this. Y'all have a good day. I'll see you tomorrow. Quiz tomorrow. Domain logarithms. Yeah.
I actually thought about this weekend. Is there any way I can still enter it in some type of a board?
Yes, do it soon.
Okay.
Okay.